Alright, in this section we're going to talk about exponential and logarithmic equations. And both of those we're going to find some different ways to do some solutions, and they're all going to kind of come back to in this chapter dealing with one-to-one properties and inverse properties. And we're going to use those to help solve some of these and make them simpler. So just a quick reminder here, one properties, we went through a couple of these already where we looked at if it was an exponential form here, if we had the same base, both of these have base a, so a raised to the x equals a raised to the y, well, if they are truly equal on each side and both of them share the same base, then that means that their exponents also must be equal to each other. In a logarithmic form, if we had a log base a equals a log base a, so again, keeping that same base going, if that's going to be true for the left side to balance with the right side, then that means the x value and the y value also have to equal each other. So that's the idea of one-to-one properties. A little review on inverse properties. And the inverse properties where the bases and the logarithms would undo each other, or the exponentials and the logarithms. We went through one, and one of the keys we said to look for was, does the base of the exponential equation here equal the base in the exponent of the logarithm? If they're the same, then the value right here becomes our solution. Now if we have a logarithmic equation or a logarithmic function, we look at the base of the logarithm and this number, and if they're the same as each other, then the same idea, the exponent itself, is our solution. So we're going to use those ideas, both in exponential and logarithmic, to solve these problems. So let's take a look at a couple of examples. Some of these will be pretty basic that we've probably covered already, but we want to hit all the bases and see that we can handle these types of problems. So one of the first problems that we ran into was one that looks something simple like this. 2 to the x equals 32. Now when we ran into a problem like this, exponential form obviously, we wanted to see, could we get this base rewritten on this side to be the same base? And in this case it does work out. 32 can be written as 2 to the 5th power. So we've got 2 to the x equals 2 to the 5th. So based on that idea of one-to-one, if the bases are equal, then their exponents also have to equal each other. So that would be our solution. So that was one that we've already dealt with before. Now another idea with one-to-one, let's do one where we have a logarithmic, and let's do a natural log. And let's say we're going to have natural log of x minus natural log of 3 equals 0. Now if we want to get the idea of one-to-one, just like we had in the exponential here where we had bases the same, we want to have matching logarithms. So we're just going to switch sides and switch signs. We're going to add natural log of 3 over to the other side. And that's going to leave us with natural log of x equals natural log of 3. And again, remember, natural log is just a log base e. So that's going to match that, which means my values that I'm trying to find also have to match each other. And there's a solution using a one-to-one property when we're dealing with some natural logs. We can set up another one that's similar to the exponential form here. It's going to take on a little bit different look because we have to do a little bit of extra work on this one. But let's say we have the fraction 1 over 3 all raised to the x power, and that's going to be equal to 9. Now again, there's more than one way to solve most of these problems that we're looking at, but we want to try to apply some of these properties just so they can stick a little bit. So one thing that we maybe would do with this one is we would take the reciprocal of 1/3, which is 3, and then that becomes the negative first power. 3 to the negative first is the same as 1/3. Well, that's still raised to the x power. Well, over here, that 9 can also be a base of 3 raised to the 2nd power. And we accomplished what we wanted. We got same bases, which means the exponents have to equal each other. So negative 1x equals 2. We can divide both sides by negative 1, and we get x equals negative 2. So there's our solution for that one. And like I said, there's probably some faster, easier ways, but right now we just want to reinforce that idea of 1 to 1. Now, another form that we can look at here, let's look at a problem that looks like this. E raised to the x equals 7. Now, on this one we want to take a look at a little bit with our inverse properties. Now again, not the only way to solve this, but it's one method. If we decide that we've got an exponent up here that we need to find, but I can't get same base, I can't get 2 to some power, 2 to some power like we did on those last problems. Well, one thing we can do is bring in a logarithm. And since this is base e, we're going to do a natural log. So on this side, I would just do a natural log of e to the x equals, and since I have to balance it, I'll have to do the natural log on the right side as well. Now because this is base e, here we go again, bases match, which means our exponent is the simplified solution of the left side, so I just get x equals natural log of 7. Again, this is an exact solution. If we had to go to the calculator, we could get an approximate solution. But for now, we're going to stick with that exact solution. So that's one method that we could use where you're going to see a little bit with one of the inverse properties happening right here. All right, let's take a look at another one. We could also start with a natural log. So let's say we're going to have natural log of x equals negative 3. Now again, there's a fast way to do this. We've already talked about how to solve something using the circle, but just to point out or bring out again that idea of one of the properties, let's take a look at this. And if we have base e, because natural log is base e, I could actually say both of these probably or potentially came out of an exponent. So let's say I had base e and this was the exponent. Well, that means I'd have to have base e on this side as well. And one way, or one reason I might want to look at this is because now again, the base of the exponential function, and because natural log is also a base e, since they equal each other, this is my solution on the left side, and I just get x equals e to the negative 3. So again, there's the application of our inverse property. Now, we've done a problem like this before where we brought out our little mnemonic and said use the circle, where we basically said there's base e, so we're going to do base raised to the exponent equals this. So e to the negative 3 equals x. So obviously if we can solve it quicker we will. But like I said a couple times already, we just want to reinforce this idea of using the properties for the time being. Now we can go one further on this one, and let's take this one as a log of x equals negative 1. And if we do the same approach as what we did over here, since this is a base 10, I'm just going to say that, again, this potentially came from an exponent, as did this. So we're going to go 10 raised to the log x, or a common log. Over here I'd have to do 10 raised to the negative 1. Now again, on this side, pretty simple, because this is base 10 and this is base 10. X is my simplified that side, on the left side, so I just get x equals, and negative 1 is actually equal to 1/10 when we pull in our reciprocal. So again, a couple different ideas that we can use with this.